Mr. Chairman, good afternoon, ladies and gentlemen. So indeed, my presentation will deal with Ti6Al4V and with some experiments we have done on this material. So why Ti6Al4V? Why this type of study? So it was what I will present today as a part of so what I will present today, the experiments I will present today were performed in the framework of a large project we have in Belgium involving all universities active in the field of material science. And it was a project on multi-scale modeling. And we were mainly responsible to characterize the materials, and maybe here I will present some results on the damage characterization and also on the fracture characterization we have done. So why Ti6Al4V? For many reasons, and one of the reasons is, or the main reason is that it is a very interesting material, not only from a scientific point of view, so it's a dual phase material, so you have a soft alpha phase, a hexagonal phase, so also very interesting from a texture point of view, from a point of view of anisotropic properties. And next to that, it also has a very interesting properties which makes that it is used for many engineering applications such as turbine blades, sport equipment, also elastic protection applications. So it has a very high strength to weight ratio, it's very corrosion resistant, and it's also biological compatible. So also in the biomedical sector you can find applications. The bad thing from an application point of view for most applications is that it is very sensitive to magnetic shear. So it's a sensitive material, but of course from a scientific point of view that's also something very interesting to study. So we studied both sheet material, so it's a sheet with a thickness of 0.6 millimeters provided by Ti6Al, and then also an extruded bar with a diameter of, yes, it was 16 millimeter. So to characterize the damage properties, the fracture properties, we carried out experiments aiming at different stress states in the material. So both static experiments, dynamic experiments. So the dynamic experiments were carried out using a split bar facility. So this means that we always had to use very small samples. This because of the testing technique. So we developed plane shear sample geometry. So plane shear, by applying a tensile load, we concentrate shear stresses in this region of the material. And what is very special of this for this geometry is that we have a slightly asymmetrically positioned notches. So during elastic deformation, we have a slight rotation of the shear region, and as soon as we come into the plastic region, we have fully aligned shear region, so it makes that we have very low triaxiality, as I will show. So then also a very classical tensile experiment, of course, a small tensile experiment, and then we also have the plane strain experiment. So plane strain, as you can see, different values of the triaxiality, different values also of the loading angle. For the extruded material, for the bar material, we carried out torsion experiments on thin wall tubes, also torsion combined with a certain level of compression, so aiming at negative triaxialities, and next to that we also did the classical, the dog-bone-shaped sample, the experiments on the dog-bone-shaped samples. So here's some results, tensile test results with the different geometries. For the sheet material, shear, the tension, the plane strain, people familiar with this, there are not really surprises in this course. So not really surprises, certainly if you have a look at the curves at the first sight. So the shear stress level is indeed the lowest level we have, the plane strain level is the highest level we have. So the blue curves are always a static, representative static experiment, and the red curves are a dynamic experiment. So if you have a further look at the curves, almost, except one experiment, almost all curves have a kind of unstable stage of deformation. So you reach a certain maximum stress level or maximum force level, and then you have localization of the strains in a very limited region around the center of the sample. One exception, the dynamic shear experiment. There we had adiabatic shear bending, so during the hardening stage, we had the lab-produced failure. So the immediate failure, no stage of unstable deformation as in the other cases. So next, we performed high-speed imaging or static imaging on the samples during the experiment and used digital image coordination to extract local information in the center of the sample and at the location where we expected the fracture. So you can see the curves over here, so that these are. And what this clears, so the evolution of the local strain in the center of the sample, the dynamic curve, the red curve is always above the static curve. So in the dynamic experiments, we had high localization of the strains. For a certain displacement, we had high strains in the center of the sample. So further localization. If we then look at the final locally measured strain value, it is clear that for almost all the experiments, the dynamic deformation is low, the dynamic fracture strain is lower than the static fracture strain. Except one, for the plane strain, we got values, deformation values, fracture deformation values, but very close to each other, so almost no influence of the strain rates. The bar experiments, here tension, torsion, very similar conclusions, and here the torsion compression, that's a very interesting one. So here without the compression, here with the compression, and what is clear, even here for this case we applied an additional compressive stress of 340 megapascal, and almost we got a gain in fracture strain of 50%. Further loading in the actual direction gave us double the fracture strength. So also in the negative triaxiality region, material is very sensitive to the triaxiality. Alright, some images of the high speed. So for the very small samples, for the sheet samples, we had a very, very beautiful, from an engineering point of view, very beautiful fracture development, and we were able to capture the fracture process. So it was really textbook. So what we observed was onset of diffuse necking, so onset diffuse neck, immediately followed by a crack in the middle. A crack slant surface was found in the middle. Then after the fracture here, then we had localized necking. Close to this region, localized necking, and there we had, we followed perfectly what you predict based on the localized necking theory. So we found an angle close to 55 degrees, as you would predict for this type of fracture. When we tested the classical standard geometry, so the classical big samples in a static case, we had a completely localized necking followed by failure. So here we have a double failure for the failure type. So in the static experiments, classical geometry, so it's clearly geometry dependent. We had localized necking followed by failure, almost no diffuse necking or not visible diffuse necking. So for the shear there, unfortunately, we were never able to capture really onset of the fracture. We hope it was initiated in the middle, but in the center of the sample, of course we never know. But of course we never know. So here, shear fracture, plane strain. What is very clear from this failure is that it was entirely aligned with the tensile direction. Because in many shear experiments, you see, you observe a fracture with a certain angle, but this is not the case because of the eccentric notches. So for the fracture of the bar, cup and cone for the tensile experiments, and adiabatic shear bending for the other experiments. We also had a look at morphology of the fracture surface. So clear from all these samples was that we had a ductile fracture. So in all the release, we clearly observed dimples in the dimples. There was a slight difference in size between the dynamic tension and the plate strain experiment, a much more pronounced difference in size of the dimples in the middle of the shear experiment. Not close to the boundaries, because there you have conditions very close to uniaxial stress, and there indeed we observed that the dimples were very close in size to the ones we had in the tension experiments. So very much in line with expectations. Image G was used to analyze the size of the dimples and fracture surface, and you can see some values there. Then we also counted the void fraction, aiming at a kind of modeling-based Gaussian type modeling where we need to have an indication of the voids, so the size of the void fraction. So what it is very clear that it is a very much triaxiality. So the voids we had very much triaxiality dependent, and the shear experiment we don't find voids, of course. It's also difficult to capture voids in shear experiment because they are closed, but we had no indication that there was any void formation. So in the plane strain experiments, much to our surprise, we almost found no voids, so much less voids than compared to the Ti6Al experiment. So then also we observed some clusters of voids in the bar experiment. We also could see that onset of the void formation was always at the interface between the alpha and beta grains. So interesting information for the modeling people. And then to come to a more in-depth understanding and to an analysis of the results I just presented, we also carried out some very basic finite simulations. So to model the plasticity, we used the Johnson-Hoop to take into account thermal softening and strain rate hardening. So plasticity, a hardening model, Johnson-Hoop, and we combined that model with the Johnson-Hoop phenomenological fracture model. And actually, much to our surprise, we obtained very beautiful results, as I will show. So here, for instance, why did we do the experiment? Why did we do the modeling work? We wanted to see what we got in the material during the fracture process. So here the plane strain sheets sample, the center of the sample. What is very clear, you can see the triaxiality here, that you only have the high value of the triaxiality around the center of the sample. So not the notches there we have, as you can expect, there you have much triaxiality closer to the unreadjusted stress limit. So for the tension bar, to our surprise, we had some negative triaxiality close to, adjacent to the network region. So interesting results. You not only have a non-homogeneous distribution of triaxiality below the angle close to the center, but of course it also evolves during the experiment. So here you can see the different experiments, even more experiments. We also carried out the head-shaped samples, but that is published, so I don't focus on this here. So the plane strain, the tensile on the sheet material, the evolution of the triaxiality as a function of the equivalent plastic strain in the center of the sample, they are converging because of the Manning phenomenon, of course. So they are converging. Also in the tensile sheet, you are going to values closer to the 0.6 you have the plane strain experiment. So the shear sheet, indeed, very low triaxiality. I don't think if you would have the eccentric, I'm not sure. If you would have the eccentric notches, you would have values much closer to 0.1 instead of the ones we are having here. So, as mentioned, much to our surprise, very simple modeling, we could capture the force elongation of the stress strain curves with the model. Much more interesting, certainly for the fracture, the damage evolution, we were able to capture the type of fracture. So as I just mentioned in the static experiments using the thick samples, the standard samples, we had localized or fracture aligned with the localized bands. Indeed, the simulation captured the type of the fracture. Next to that, for the small samples, the Hopkinson samples, we also found the combined fracture types. So slant fracture in the middle, more on that later, and also then the bands according to the localized length. Also for the dynamic shear, captured the fracture as we had in the experiments. So that's here an image, an SEM image of the sample of the thickness direction. That's the thickness direction 0.6, very thin sheet. So here you see in the middle the slant fracture, and this is completely in agreement with the simulation. Here also the thickness direction with the equivalent plastic strain. So indeed concentration in the middle, you have the banding, and here the triaxiality, the highest triaxiality in the middle, and then values smaller but still high in that cross-like structure as we have it in the fracture surface. So we were able to capture what we had. Then we also looked at triaxiality, so rather classical curve, the evolution of the triaxiality, where we had onset of the fracture during the experiment. So here you have the strain, the fracture strain as a function of the triaxiality for the different experiments. If we would have done only these experiments, then we would have very nice results. So a decreasing fracture strain as a function of the triaxiality, Unfortunately, we have those experiments. So the tensile sheet material and also the tensile bar material had fracture strain much higher than the one you would expect, the ones you would expect according to that curve. If we then look at the dynamic cases, so dynamic fracture strains close to the static ones, a little bit smaller, but pronouncedly lower for the torsion and for the shear experiment because of the adiabatic shear bending. So further we then focus on these experiments. Why do we have a fracture strain in the tensile experiment, which is much higher than actually the value you have for the plane strain experiment? What is already clear from this figure is that the evolution of the triaxiality, so starting at a lower value for the tensile experiment, higher value for the plane strain experiment, that you should take that into account in your modeling. So it's not only the end result is important. So here you can see the voids. So the fraction of the voice, the size of the voids, and also the fracture strain we got for the tensile and the plane strain experiment. So the red one is the plane strain. So the lower fracture strain, the size of the voids, very similar in both experiments. But when you look at the fraction, then it was really clear that for the plane strain, in agreement with, of course, the lower value of the fracture strain, that indeed we had lower fracture. We had lower fractions of the voids. So we further analyzed this, taking into account the simulations, and what we found was that in the tensile experiment, very close to the fractured surface, we had a very pronounced gradient of the strain. So close, here we had a value of 0.5, 50% of strain. If we move away from the fractured surface, 200 microns away, so it's not really far away, but 200 microns away, this value, the value of 50%, dropped to 30%. If you move further away, if you go to 300 microns, your value is almost half. That information, the evolutions, the gradient of the plastic strain, we plotted the void fraction, we counted as a function of the plastic strain, and we got the curve like that. So our conclusion from this is that you need, as a matter of fact, you need a certain threshold value of the strain to have void initiation, to have nucleation of voids, and that you need triaxiality to go to a fracture to have growth and coalescence of the voids. So in the plane strain experiment, the hypothesis, of course, in the plane strain experiment, we had failure at the value of almost 30%. So there you have onset of void nucleation immediately followed by coalescence because of the high triaxiality. In the tensile experiment, you still have time, because the triaxiality is lower at the moment, you have time for the voids to grow and to coalesce. So this is my conclusions.
So thank you.